Here we're going to introduce one of the most widely used approximation theories in quantum mechanics, perturbation theory. Perturbation theory is useful to us because there are many situations in quantum mechanics where important and useful phenomena occur even when we're making relatively small changes. As I said, one scientific example is the effect of electric fields on atoms. The fields that we can practically apply are very small compared to the fields inside the atoms themselves. So our applied perturbation is small. Despite that, we can quite easily see the consequences, for example, in the splitting of spectral lines, the so-called Stark splitting. Perturbation theory is, at its core, a theory of successive approximations. We essentially can calculate the first small changes we make based on the properties of the unperturbed system. This kind of approach is also common in classical systems. Perturbation theory is by no means restricted to quantum mechanics. Indeed, most situations in classical physics where we pretend the problem is approximately linear for small displacements have much in common mathematically with perturbation theories. If we want to calculate how easy it would be to stretch a spring by a small amount, we do that calculation based on the shape and properties of the spring before we stretch it. That is a situation where we can calculate the change we get based on the mechanical properties of the unperturbed system. This would be a first-order calculation. Of course, if we pull the spring by some amount, we may in fact change how difficult it is to make further changes, just like trying to stretch an elastic band too far. So when we start to stretch the elastic band, it's relatively easy to stretch it, and the amount it stretches is probably roughly proportional to how hard we pull. But if we pull too much, the band gets very much harder to stretch. So we have to take account of that in our theory, that as we stretch it, it gets harder to stretch it. And that is not something we can do in a simple first-order linear theory, and we might have to think about quadratic or second-order terms in our theory. We have to use a theory of successive approximations. We have to put in the fact that by stretching the elastic band, we've somewhat changed its properties, and we have to put that into calculating what would happen if we try to stretch it some more. Another good example of a spring-like system is a loudspeaker cone. To a first approximation, the amount that the cone moves in and out is proportional to how hard you drive it by passing an electrical current through the magnetic coil. But the movement of the loudspeaker cone is not quite linearly proportional to that drive. The plot of how much a loudspeaker cone moves in and out in response to the current we feed into it might not be exactly a straight line. Most likely at high drives, for example, if I push in too far here, the loudspeaker cone can't go any further. And that line, therefore, of the output versus the input is something that would have to bend over. And we might have to describe that line not as a straight line, but as some higher order polynomial. And these particular saturations of the behavior would introduce, for example, cubic components, representing the fact that there's only so far you can go in either direction. Such higher order behaviors can give rise to quite specific effects, such as harmonic distortion in loudspeakers, generating new frequencies in the sound that were not there in the driving current. And they can be calculated by theories that have the same basic mathematical flavor as perturbation theories. Perturbation theories are ways of formalizing these ideas of successive approximations or polynomial behavior of the response to some drive. And we'll now start to set up a perturbation theory for quantum mechanics. In quantum mechanics, it's particularly common to want to know the change in the eigenenergies as we apply some perturbation or small change to a quantum mechanical system. So we will discuss our perturbation theory for energy eigenvalues and eigenfunctions. This means that we will be considering the Hamiltonian of the system and imagining we're going to be changing the system slightly by slightly changing the Hamiltonian, or as we will be describing it, by adding a perturbing Hamiltonian. For the moment, we will be doing this for problems that are not changing in time. Hence, this theory will be called time-independent or sometimes stationary perturbation theory. We will only be considering here the case where our energy states are non-degenerate. That is, there is only one eigenfunction for one eigenvalue. We can construct perturbation theories for degenerate cases, and these are actually quite important. But for the moment here, we're going to avoid them because they turn out to be rather different in character. Now, at this point, I should warn you that the first time most students go through perturbation theory, they find it very confusing. There are a lot of subscripts and superscripts involved, so the algebra is necessarily somewhat complicated. Also, for many modern students, it's the first time they've looked at a theory like this, one based on what are essentially power series approximations to quite complicated problems. Before modern computers become available, workers in fields such as classical and even quantum mechanics were very used to making such analytic approximations because fully numerical calculations were hard to perform. But you might wonder again why, therefore, we are bothering to look at such an analytic approximation theory now that we have very sophisticated abilities to calculate, and why, therefore, we're taking this time to go through what can initially be a very confusing subject. Again, perhaps the most important reason here is for conceptual understanding of processes in quantum mechanics. It's also true that in many cases, these approaches enable us to come up with quite simple and generally useful formulas, which will save us much time in calculations. So, please bear with me as we construct what initially can look like quite formidable and forbidding formulas.
So formally then, we're going to construct time-independent perturbation theory. We start out by presuming we have some so-called unperturbed Hamiltonian, H0, and that has some presumably known and normalized eigensolutions. So here's H0 operating on its eigensolutions, some particular psi n with an eigenenergy En. Now, we imagine that our perturbation could somehow be progressively turned on. This isn't in a time-dependent sense, it's really in a mathematical sense, that we could progressively make our perturbation stronger and stronger mathematically. And, for example, we might be imagining that we are progressively increasing some applied field or voltage on some structure. And we would imagine increasing it from 0 to some specific value. So we could look successively for changes in the solutions that we're going to see, for example, in the mth energy eigenvalue, Em. So here's what it is to start out with. We've called it Em with a superscript 0 here, and at 0 field we presume it starts out at some value here. And then perhaps, first of all, as we turn on our field here, the eigenenergy changes linearly with field. So this is our eigenenergy here on this vertical axis, and as we turn the field on, perhaps with some proportionality constant, A, the eigenenergy, for example, maybe increases. So that would be a change in eigenenergy that was, at least for small fields here, proportional to the applied electric field, for example. We would call those first-order corrections to the energy. So we're saying the energy is equal to some constant, we could call that the 0th order result, plus some change in the eigenenergy that's somehow proportional to the amount of perturbation that we're putting onto this system. Of course, that might not be quite enough. The change of energy E with field might not be linear. Perhaps there's some part of it that's proportional also to the square of the field that would give some curvature, for example, to this line we have here. And we would call the additional changes that were proportional to the square of the field, we would call those second-order corrections. And we could keep on going with this to higher and higher orders. Now, it's more convenient and general to imagine that we actually physically have a fixed perturbation, for example, a fixed applied field, E, but instead we mathematically increase what is typically called a housekeeping parameter, gamma here. So gamma is going from 0 up to 1, and as it does so, that means that mathematically we're increasing our field from 0 up to this specific value. That's one way to think of it anyway. So our perturbation at any particular point on this graph here is really gamma times E. And E, we said, we imagine is actually fixed, and this is just a mathematical parameter that we're looking at here. So now we can express changes as orders of gamma, gamma to the 1, gamma to the 2, and this one incidentally would correspond to gamma to the power 0, rather than changes that are in the field itself. So this is merely a mathematical change compared to what we were thinking about previously. But this is the way that perturbation theory is typically written down, even if at the moment it seems somewhat unnecessary to make this mathematical change. So instead of writing that the eigenenergy is the initial value plus something proportional to the perturbation plus something proportional to it squared, we write instead the initial value plus gamma times some constant here plus gamma squared times some other constant here. This constant is really taking the role that the A took there, and this one is really taking the role that the B took there. But instead of working out A and B, we're actually going to work out these parameters, EM1 and EM2, and so on. These terms here have dimensions of energy. Gamma is a dimensionless quantity. And they reflect the first order and second order corrections to the energy that result from this specific perturbation that we're putting on here, for example, a specific value of field. In general, then, we imagine that our perturbed system has some additional term in the Hamiltonian, and we call that the perturbing Hamiltonian. So far I've talked about applying some electric field that would therefore correspond to some perturbing Hamiltonian. In this theory, we're a bit more general than that, but we imagine that we've somehow made a perturbation to the system that corresponds to adding in some perturbing Hamiltonian to the Hamiltonian of the system. So, for example, in the case of our infinitely deep potential well with an applied field, that perturbing Hamiltonian would be this expression here, the electronic charge times the field, times basically the position, although we've referred the position to the center of the well. That's not particularly important, but that's a formula we chose to write down here. So that would be our perturbing Hamiltonian. You see it has the dimensions of energy in it. And in this theory, we write the perturbing Hamiltonian as gamma times the actual perturbation we're finally going to be putting on here. That's the notion, anyway, mathematically. And we use gamma to keep track of the order of the corrections that we're talking about. And we do that by tracking the different powers of gamma in the various expressions we come up with. And of course, once we've done that, conceptually at least, we can set gamma equal to 1 at the end of all of this if we like to. So we could have set up the theory this way, and it could still be a perturbation theory. There would be nothing wrong with that, in which case we would work out A and B in some way or other, and possibly some other parameters. But to make it more general and to correspond to the notation that's typically used in discussing quantum mechanical perturbation theory, we're going to write in this form instead, and we're going to work out the parameters EM1 and EM2 and possibly some others. If this is confusing at first, then just think of gamma as the strength of the electric field in our specific problem. With this way of thinking about the problem mathematically, we can write our perturbed Schrodinger equation in the following way. So here's our original unperturbed Hamiltonian, and here's the perturbation we're adding, and formally we put in this gamma housekeeping parameter in front of it. And that is the total Hamiltonian of the system, and it's acting on the wave function, and the idea is we're going to figure out the eigenenergies, E, of the system corresponding to some solution wave function here. So we now presume that we can express the resulting perturbed eigenfunction and eigenvalue as power series in this parameter gamma. That is, in the following kind of form. So the function we're talking about, we think of it as some zeroth order function plus some function proportional to gamma plus some other function proportional to gamma squared plus some other function proportional to gamma cubed here. And similarly for the energy, we imagine it starts out as some constant plus something that's proportional to gamma plus something that's proportional to gamma squared plus something that's proportional to gamma cubed. And as I said, if the housekeeping parameter seems a little abstract, just think of gamma as a dimensionless measure of the strength of the field that we're applying in our specific problem, for example. Now, what we do mathematically is we substitute these power series into our perturbed Schrodinger equation. That is, in this equation here, we're going to substitute this power series for phi into this equation here and here, and we're going to substitute this power series for e for the e here. And that gives us something that looks like this. So here's our Hamiltonian, and here's our wave function phi. We get it on the left and also over on the right, written out as a power series. And here's our e, also written out as a power series. Now, at any specific point in space, each of these functions, with the superscript n's in here, corresponding to what we call the orders of these functions, and each function of this form, remember that the Hamiltonian acting on some function is just a function. If you think of this as a matrix and think of this as a vector, multiplying the two of them together gives us a vector. So this also is a function. So we think that at any specific point in space, this function and also this other function here is just some number. It has a value at a particular point in space. So at any specific point in space, the left-hand side of this equation is just a power series in gamma. For example, something that looks like this. And so is the right-hand side. It's also just a power series in gamma. So that is, we choose some point in space. Each of these functions has a specific value, but we're operating on them with this operator here. So it's this whole function that has some value at a point in space. But on the right-hand side, we simply have the values of these functions at this specific point in space. But therefore, at any point in space, we have a number from the left-hand side and we have a number from the right-hand side. So this is a simple equation between two numbers, and we can write those numbers out as power series. So it's an equation between two power series. Because a power series expansion is unique, the only way that two power series can be equal to one another, like these ones here, and that can work for every value of gamma, at least within some convergence range, for example, between 0 and 1, is if the series are equal term by term. That is, if A0 is equal to B0, A1 is equal to B1, A2 is equal to B2, and so on. That's the only way this can work, because power series have to be unique. Hence, in this expression here that we've just written down, we can equate each term with a specific power of gamma. That is, we find terms of the specific power of gamma on the left, then they have to be equal to the terms with the same power of gamma on the right. And hence, we can obtain a progressive set of equations which we can solve to evaluate corrections. So we're going to look for equations equating gamma to the power 0 on the left with gamma to the power 0 on the right, gamma to the power 1 on the left with gamma to the power 1 on the right, and so on. And we can do this to whatever order we wish. We can keep on going terms in gamma cubed, gamma to the 4th, and so on. So therefore, in this equation here, for example, starting with gamma to the power 0, that is, terms without any gammas in them, we equate the ones with no gammas in them on the left to the ones with no gammas in them on the right. So that would give us our 0th order equation. So if we have to have no gammas on the left, we have H0 phi naught is equal to E0 phi naught. Any other terms on the left would have a gamma in them, and any other terms on the right would have a gamma in them. And this, of course, is just the unperturbed equation. We already know the solutions to this equation. And we know, therefore, that phi 0 is actually just one of these original eigenfunctions. And E0 is just one of these original corresponding eigenvalues. So if we now presume that we're starting in a specific eigenstate psi m, and we'll take that presumption from this point onwards in this derivation, then we're going to write psi m and En instead of phi naught and E naught. These are the same thing, so we're going to change over to this notation now. So with our equation now rewritten with our new notation, we've got psi m here instead of phi naught, and we've got Em here instead of E naught, and also psi m here instead of phi naught. We can set up a progressive set of equations, each equating a different power of gamma on the left and on the right. So our first one, the one we already have, is h0 times psi m is equal to Em times psi m. Any other terms on the left would have a gamma in them, and any other terms on the right would have a gamma in them. The next one we get by equating gamma to the power 1 on both sides. So we could have h0 times gamma phi 1, and we can have gamma hp times psi m. So here are those two terms. And then on the right-hand side, we can have Em times gamma phi 1, so that's this term, plus gamma E1 times psi m, that's this term. And of course, we can drop the gammas through all of these terms, because they all have a gamma in them. And we can keep going. The second order, we have h0 operating on gamma squared phi 2. We have gamma hp operating on gamma phi 1. And on the right-hand side, we have Em times gamma squared phi 2 and E1 times gamma phi 1 and gamma squared E2 times psi m. And again, we can drop the gamma squareds on both sides. And we could keep on going like this. So we've separated out 3, and more if we want them, different equations by equating powers of gamma on both sides. We can rewrite these equations slightly. It's a simple manipulation. So this equation we will rewrite as this one here, h0 minus Em times psi m equals 0. Now, incidentally, you see we're using the same loose notation here as we've used before. This is an operator, and this on the face of it is just a number. If you like, you can put in an identity operator here. But typically in quantum mechanics, it's presumed that we understand what is going on here, and we're not confused by it. The first order equation we can rewrite rather simply as one in this form. So again, we've taken the same kind of operator on the left, but now operating on phi 1, and on the right we'll have E1 minus the perturbing Hamiltonian times psi m, with the same understanding about implicit identity operators, if you like. And for the second order one, a rearrangement can give us, again, the same kind of form on the left, and now two terms on the right-hand side here. And we can keep going with that.